everyone, this is Professor H. Rahman from Agriculture and Food Engineering Department, IIT Kharagpur. I welcome you all to this lecture on measurement of soil strength, cohesion and angle of internal friction. So, the concepts which will be covered is what is soil strength, cone penetrometer, how it is related to soil strength, and cohesion as well as angle of internal friction. Now, we define soil strength as its ability to resist deformation or failure. How well it can withstand the external forces which are acting. It could be due to compression, due to shear, due to adhesion, due to frictional length. So, cone index is used as an indication for measuring or indicating the soil strength. So, what is a cone penetrometer? Basically, a cone shaped probe is forced into the soil and we define it as the force per unit base area which is required to penetrate a cone shaped probe into the soil at a steady rate. The rate is around 30 millimeter per second. So, the strength, that is the force per unit area, that means if force is expressed in kilonewton and area is meter square, then kilonewton per meter square will be the unit of cone index. Though it says cone index, but it has a unit of pressure, and this is measured with the help of a cone penetrometer. So, there are basically two types of cone penetrometer. One is static cone penetrometer, the other one is impact type cone penetrometer. And whether it is static or impact type, the cone penetrometer will have a base, cone base at the bottom, then there is a rod and there is a proving ring with a pushing handle or a stopcock. So, in case of a static penetrometer, the one which is shown in this figure, this has to be forced into the soil either by a human being or by hydraulic pressure, so that what is the resistance which is offered by the soil, that will be recorded either manually with the help of this proving ring, or you can directly put sensors so that you can record it for each unit of depth, maybe at an interval of 1 centimeter, even 0.5 centimeter is also possible. But usually a manual run static cone penetrometer, it has some graduations provided on the side, on the rod. So, at an interval of 1 inches, and the cone area is around, base area is around 3.23 square centimeter, and the cone angle is 30 degree. So, if it is a impact type penetrometer, then a pointed device is with a certain mass that has to be dropped from a certain height, and then you measure what is the corresponding depth of penetration. So, there are two types of impact type cone penetrometer. One is the pointed device is to be dropped from a certain height. The other one is the pointed device is to be kept vertically on a soil, then a mass of known weight which has to be dropped onto this, and the number of drops required to cause unit of penetration, that is recorded. So, if it is a static penetrometer, then there are certain standards which are given by American Society of Agricultural and Biological Engineers. What should be the base area, what should be the base diameter, and the rod diameter. So, if it is for soft soil, then the base area should be around 323 millimeter square, and base diameter is around 20.27 millimeter, and the rod diameter is 15.88 millimeter. If it is a hard soil, then the base area is 130 and millimeter square, and base diameter is 12.13 millimeter, and the rod diameter is 9.53 millimeter. These are the standards given by American Society of Agricultural and Biological Engineers. So when it is pressed into the soil either manually or by a hydraulic power, which is shown in this figure in the right corner, so we will get a plot like this. That is the cone index. In fact, this is the resistance which will be recorded, then resistance divided by the cone base area, resistance divided by the cone base area will give you, divided by the cone base area, which is nothing but 3.23 square millimeter, square centimeter. So that is indicated as cone index. So when you plot cone index versus depth, so the nature of the curve, I have just a sample of the curve I have indicated. Then question arises, how to measure this resistance? We can put a load cell so that you can directly take the output from the load cell. Then once you calculate, then the load cell has to be calibrated, and after calibration we can find out what is the corresponding cone index. Now this has to be pushed into the soil up to a depth of minimum 150 millimeter. Nowadays we can go up to whatever depth we require, up to that we can go. So you will get a plot like this. If you get a plot like this, then how to find out the average cone index? So average cone index will be the area bounded by this curve. So we draw a horizontal line, then what is the area which is included? So that can be calculated with the help of a graph sheet. Then you can divide with depth. So that will give you what is the average cone index. So based on cone index value, we classify soil into three types. One is soft soil, medium soil, and farm soil. Soft soil is around 450 to plus or minus 50 kilopascal, and medium soil is 1000 plus 100 kilopascal plus or minus. Then farm soil is 1800 kilopascal plus or minus 100 kilopascal. So based on this cone index, we try to classify the soil. When we use two types of penetrometer, like static cone penetrometer or the impact type cone penetrometer, we use two different models for expressing the cone index. One model is using the energy required to cause penetration, which is nothing but your impact type, how much force mass is dropped to a certain height. So that will give you how much energy is required to cause penetration. But in case of a static cone penetrometer, we measure force, then we divide by area. So there are basically two models which are used. One is using energy required to cause penetration, other one is force required to cause penetration, or force per unit area required to cause penetration. Cone penetrometer readings are affected by moisture content, and it is affected by the ball density. So you have to mention what is the moisture content at which you carry out this test. Then in addition, if you want to find out the average cone index in a plot, there you have to indicate we have to measure the cone index value at different places. Then you have to express the average with a standard deviation you have to mention, and with the coefficient of variance. So on the right corner you can see how the concept probe, this one, concept probe is fixed onto a hydraulic cylinder. This is a double acting hydraulic cylinder, and the hydraulic power is taken from the tractor. Now comes shear strength. Resistance to deformation by continuous shear displacement of soil particles subjected to shear stress. Why you are interested in this? Because the wheel, when it starts running, that will create some shear displacement at the interface of soil and wheel. So that's why you are interested in measuring the shear strength. So shear resistance occurs due to structural resistance, due to frictional resistance, due to cohesion and adhesion. And shear strength particularly is governed by two factors. One is your internal friction, the other one is cohesion. So usually we follow the Coulomb's equation, which says that shear stress is equal to C plus normal stress into shear stress will be equal to C plus normal stress into tan phi. So if you multiply the contact area, then it becomes, I multiply both these sides with area A, so that becomes F, it's a thrust force. So we denote it as maximum thrust, this is tau max. Maximum thrust force will be equal to AC plus W tan. If you look at this equation, Coulomb's equation, I have converted to F max is equal to, F max means maximum thrust which is developed is equal to AC plus W tan phi. In this equation, the maximum thrust which is developed is a function of cohesion, is a function of angle of internal friction, is a function of the contact area, is a function of the weight which is coming on the wheel. Now, if it is a sandy soil, cohesion less sandy soil, that means C has no role. So now thrust maximum which is developed is a function of cohesion, it is a function of angle of internal friction, it is a function of contact area, it is a function of weight coming in the contact area. Now, if it is a cohesion less sandy soil, that means C is 0 and phi has some value. So, there the maximum thrust will be dependent on W itself, where the area has no role. Now, if it is a clay soil, that means phi is 0, so obviously the maximum thrust which is developed is dependent on the contact area. So, these are the two extreme conditions which I represented. Now, how to measure the shear strength of soil? You can measure directly in the laboratory, or you can measure in the field. In laboratory, what you have to do is you have to collect the soil sample, then you have to make cylindrical specimens by using direct shear test or triaxial compression shear test or unconfined compression test or vane shear test. We can measure the shear strength of soil. But since our will be mostly in the field, so that's why we will be concentrating on what are the apparatus available which can be utilized to measure shear strength in the field. So there are two apparatus available, one is shear annulus, the other one is direct shear test. So direct shear test is the equipment which is available for direct shear test and the equipment which is available for the direct shear test in the laboratory, they are different. Now, this is the shear annulus. Basically, this is a annular ring with fins at the bottom. This has to be rotated. This has to be pressed into the soil. Then it has to be rotated so that how much torque is required to cause failure of the soil, that has to be measured. So, if the annulus ring has an outer diameter R0 and an inner diameter Ri, and it has a width, the fin has a width of B and the height of fin is H. So, the total diameter is indicated here as D. Then we have to find out expression how much torque is required to cause shear. Now, if I take the cross section where the soil is going to be disturbed, so this is the cross section where the soil is going to be disturbed. Now, if I take a small angular radius so correspond to d theta at a radius r, so r d theta will be this length, and for an incremental length of dr, so the area of the small element will be r d theta into dr. This is the area. Now, if S or tau F is the shear stress which is applied, then this shear stress into dA will give you the shear force. So, tau F into dA will give you the shear force which is acting. This shear force is acting at a distance r. Now, the moment which is acting at the center will be moment acting at the center will be equal to shear force into the radius r. So, if T is the torque, so torque will be equal to shear force into the radius. Shear force is shear force into radius. So, shear force is your tau F into dA and radius is r, dA is equal to tau F into r d theta dr into r. So, I can write this as tau F into r square d theta dr. So, this is the incremental, this is the torque which is acting in the smaller element. Now, if you want to find out the total torque which is acting because of the rotation of the annulus ring, then we have to integrate this expression from 0 to 2 pi and from r inner to r outer, r inner to r outer 0 to 2 pi. So, that way we will get an expression T will be equal to, torque will be equal to 2 pi into tau F into r 0 to the power 3 raised to the power 3 minus r I raised to the power 3 divided by 3. So, this is how we get the expression. Now, from here if we can measure torque, then shear stress can be calculated. So, shear stress will be equal to 3T by 2 pi r naught q minus r I q. So, this is how we arrived at this equation. So, this has to be rotated at a steady rate. It is not that once you rotate then leave for some time. So, that is not allowed. Next is in situ direct shear apparatus. Now, it is a rectangular plate with having fins at the bottom. This has to be pressed into the soil and then it has to be moved forward. So, what we measure here is what is the weight which we apply and what is the corresponding area on which this weight is applied. Then we measure the tangential force F and the corresponding shear stress which is caused. So, that area if you measure, then we can find out, we can correlate this shear stress with displacement or shear stress with normal stress. So, normal stress in this will be equal to W by area will be equal to W by B into L and shear stress will be equal to, this is normal stress and shear stress will be equal to F by, again the area which is sheared is nothing but this area below this area. So, again this is B into L. So, that will give you shear stress. So, if you try to plot shear stress versus normal stress, then you will get a kind of curve which will be shown in the next slide. Now, if there are two conditions which are given, which are shown here, one is in the soft soil, the other one is the hard soil. In the soft soil you can see the soil is not displaced, there will be pockets in between, whereas in case of a hard soil the entire soil mass is sheared. That is the difference. Now, when we try to apply the tangential force, then what we measure also is the strain. So, if you plot stress versus strain, there will be getting a nature of the curve either A type or B type, which is shown in this figure, or C type. A type means for a very hard soil, compacted soil, you will get a clear cut point where you will get the peak shear stress, and after that the soil fail and it will start coming down. Now this is the case for compacted dry soil. Now for loose soil, we will get the stress versus strain curve will be like this. It will be initially rising at a faster rate, then slowly it will slow down and it will reach to a peak. So these are the two extreme curves, A and B. So in between, when the soil is behaving neither too compact or not too loose, then you may get a curve like this, where the nature of the stress and strain curve will be, it will first increase, then reach to a peak, but that peak is not as prominent as you get in case of hard soil or the dry soil, but you will definitely get a peak. Then after that the failure starts and it goes down, the shear stress goes down. So these are the three typical curves which are experienced in the field. Now when you try to plot this shear stress versus normal stress, then what we observed is you will get a straight line. So if you best fit the line, then shear stress versus this side is shear stress, this side is normal stress. So you will get point like this. So if you best fit this line and extend it to touch the y-axis, the intercept will give you the value of C and the slope will be the value of phi. So C is nothing but your cohesion and phi is the angle of internal friction. Now C, as the name indicates, is a cohesion. It has a unit which is same as that of a stress. So basically C can be defined as the shear stress when the normal stress is 0. That means cohesion is the force that holds the particle together in a material irrespective of the normal pressure exerted on the particles. Now phi, which is called the internal friction angle, is the force that resists motion between the particle while it undergoes deformation. So these are some of the ways by which we can measure shear strength of soil, and from the shear strength we can find out what is the value of C, and then we find out what is the value of phi in the field. So the reference books we can take as soil dynamics in tillage and traction, then terra mechanics and off-road vehicle engineering, then off-road vehicle engineering principle. These are some of the books which can be looked into to further enhance your understanding. So in brief, what we have done is we tried to explain what is the strength of soil, how do we measure the strength of soil, then we try to find out shear strength of soil, and how to find out cohesion and angle of internal friction from this shear strength. That's all. Thank you.